So it's my pleasure to introduce you Douglas Eck. He's professor at University of Montreal, and actually we are co-supervising a PhD student in machine learning and music, and that's so we work together often. He's interested not only in music, but in general in machine learning and sequence processing, and there's a lot of interesting problems to solve there. But music is, of course, a good problem as such. So I think with that, Douglas, I'll let you
Thanks.
on.
Is that off? Can you hear me? Okay, it seems to work. Okay, so thank you for coming. As Sammy said, I'm from the University of Montreal, Computer Science, and International Lab for Research in Brain, Music, and Sound, PROMS. And I'm going to talk a little bit about automatically tagging audio using supervised learning. And the overarching goal is to see what kind of information we can extract from MP3s and waves on the internet. What kind of picture can we paint of what's going on musically on the web? So there's a number of people that worked on this project. Students, Norman Casagrande, who's now at Last.fm, two other students who are still in my lab, a colleague, Balazs Kegel, and I'm currently visiting professor at Sun Research Labs, and I'm collaborating with Paul Lemaire in Boston. However, the work I'm talking about today was done at University of Montreal. So the structure is straightforward. I'm going to give a very short overview of sort of machine music listening and talk about audio feature extraction. And then I'm going to move into some boosting-related work having to do with predicting artist and genre from audio features, and then predicting arbitrary tags from audio features. But first, okay, a quick overview of what's happening in the world in terms of music. There are really three commercial approaches to finding information in audio and linking it to users via collaborative filtering or just having a picture of what's going on inside of an audio file. There's, of course, collaborative filtering. I presume most of you are familiar with the basic concept. So Amazon.com does this, and as far as I know, they treat books like they treat music. So they're looking at buyer preferences. The upside, of course, is all the upsides of Amazon. And the downside, I think, for music, as opposed to with books, songs are multi-purpose. So the same song on a disc can serve the uses of a dinner party or jogging or whatever. But they're only purchased once, so it's hard to untangle this multimodal usage. Whereas, by and large, a cookbook is used for cooking, and a mystery novel is used for reading on the beach. Last.fm has become very popular. It's a social recommender. And it does a better job of predicting current musical tastes because of the constant tagging that's happening at Last.fm. It also gives a good measure of popularity, but suffers from cold start for the same reason. New songs don't have any tags, and so at Last.fm, we don't know anything about new songs. And also, a problem they fight with a lot, all roads lead to Radiohead, which is to say there's a kind of popularity bias in social tagging systems where very popular groups tend to draw in other bands. And finally, there's Pandora, content-based recommendation. However, it's human-labeled. I actually think this is incredible. But Pandora does content-based recommendation from audio, but they do it by having around 40 experts listen to music and then label, take a piece of paper out and label a number of parameters. And so according to the guys at Pandora, they're doing about 7,000 songs a month. And so it's needless to say, not very scalable, right? Like, what if they want the 401st feature, right? Do they have to go back and listen to these 50,000 songs again or 100,000 songs? Okay. That's not really what this talk is about. I just wanted to give you a basic idea of the technologies that are available. I'm proposing another, really, I think, more modest approach, which is to ask the question, what can we do with machine learning? What kind of information can we extract from audio? And in what ways can we map acoustic features onto classes or distributions? Maybe we have labeled data, maybe we don't. And in doing so, how can we take audio, which is largely invisible to sort of text-based search engines? What can we extract from audio so that we can expose some of this audio structure to a search engine like Google? So This could mean automatic annotation or auto-tagging, which I'm going to talk about today. It could also mean looking for something a little bit more abstract, like some meaningful space in which to measure similarity among audio, or some meaningful space, low-dimensional space, in which to visualize audio. But one of the main goals is to be able to sort of augment and regularize social tags and other web data, so that if we take a new song, a song that I made at home on my computer, a search engine can maybe do something meaningful with that. It can extract some information to bootstrap its insertion into some search space. So the pros of something like this, I think, are clear. It's clearly more scalable. In the same month that Pandora can label 7,000 songs, we can label a lot, millions. And we can also predict attributes that are not likely to be tagged by humans, like tempo, was the recording highly compressed, values that may mean something in terms of music similarity, but which aren't sort of evident to a human who might be doing some tagging. The cons are also evident. Acoustic features are not predictive of everything, right? We're not likely to find a good feature that's going to tell us whether something is protest music or not, unless we also have the lyrics. And also, we don't have a very good measure of quality. So we may be able to say with high reliability that a particular song is 1960s bebop jazz, but we're probably not going to know that it's a great jazz solo as opposed to a mediocre one. So we may treat John Coltrane like all the others. And the final con is really difficulty for me, not for you, is that the engineering is a challenge. So in the university, constructing the databases of music, linking those databases of music to tag and other web-based textual information, doing the large-scale machine learning of extracting features and learning is a challenge in academia. And it makes Google a very attractive place, I might add, that you have all of this infrastructure ready to go. OK, so I'm going to have to speed up a little bit, I think. So this is, for those of you who do machine learning, this is extremely simple diagram. For those of you that don't, just want to give you some pretty pictures to look at to give you an idea of what I'm trying to do. I'm taking a waveform, an audio waveform. We're looking at number 1, feature extraction, extracting some sort of feature from that audio. It's probably some sort of Fourier-based feature extraction. It could be a wavelet-based extraction. Basically, there's a big toolkit full of transforms that we can try. And then we're going to take that feature, and we're going to train a classifier. In the research I'm talking about today, we're using a very simple supervised learning approach. So we have some features that are extracted from audio, and we have some tags that we've found on the web via data mining that we know relate to the audio. So we have some tagged audio. And we're going to build a classifier that will try to predict those tags from the audio. And that'll give us a trained model. And then from there, we can take unseen features, songs we've never heard before that have never been tagged, and we can generate tags for them. We might say, oh, that's rock, or I like to jog to that, or any number of other sort of qualitative features. So this is an area that's actually received some research in machine learning and also in music information retrieval. The challenge is, this is a reiteration from the previous slide 2 ago, what features do we use, how do we learn, and how do we scale? And the previous models, I think the 2 that warrant serious discussion is the work of Dan Ellis, using support vector machines from Columbia. There was some work using decision trees and some nearest neighbor algorithms, and then our work using AdaBoost, Bergstra et al. Bergstra, Casagrande, and Erhan are all students in my lab, and Balazs Kegel is a fellow professor. And the approach I'm going to talk about today is an extension of the 2006 machine learning paper using AdaBoost, where we're going to iteratively apply feature selection to build a relatively small feature set. We're going to boost simple classifiers on these individual features and combine them to predict tags. And we're actually going to treat all of these tags as statistically independent, even though they're not, to simplify the learning problem as a first step. So I'm going to go through some of the basics of feature extraction. Then I'm going to go through a little bit about boosting. It's not my model. It's a very simple machine learning. It's sort of the first thing to try in terms of doing classification. And then I'll show you some results. So I think For music-based work, the feature extraction is a very interesting problem because we want to extract features from audio which reveal musical content. And by and large, at least in the music information retrieval community, many people have started with speech recognition features, features that prove to be useful for predicting speech from audio. And from this chunk of work, I've sort of focused on three major categories. There's a whole tree, a whole forest full of ways to do this. But for those of you that don't have this background, we can look at spectral features. So basically features that make one transform from the time domain into the frequency domain, like a spectrogram. We can look at cepstral features, which are effectively a second Fourier transform of spectral features. For those of you who aren't familiar with cepstral, it's a play on words. Maybe you can figure out what the play on words is. It's spectral backwards. The stem of the word is spec backwards. So we have cepstral coefficients and some other special cepstral coefficients called Mel frequency cepstral coefficients, and a similar class of features that relate to autocorrelation. And then we have a third class of features, which I just sort of throw into a bag of statistical features that are extracted directly from the waveform, such as zero crossing rate, the number of times the waveform crosses zero over a span of time, linear prediction coefficients. There's a family of features. And so to give you a couple of examples, sort of an intuition for how we might see structure via these features, here are a couple of spectrograms. And the frequency scale is logarithmic, so they're log spectrograms, similar or equal to something called a constant Q transform. And you can see on the left we have the Beatles song Hide Your Love Away versus a Chopin waltz. And you can imagine we're seeing information having to do with pitch. We're seeing information showing that there's a voice present on the left and not on the right. And we can imagine that we can learn some things from spectral features like these. Cepstral features move back from the frequency domain into the time domain. And actually what I'm showing you here are autocorrelation coefficients, which are very similar to cepstral coefficients. We're just dropping a log transform. And we see temporal order now. We see where rhythm lives, what tempos are active in a piece of music, etc. And so to give you an overview here, hopefully illustrative, the song Pink Floyd's Money. On the top we have particular kind of cepstral set of coefficients, Mel frequency cepstral coefficients, which are very popular in speech. We have autocorrelation coefficients, and on the bottom we have the spectrogram. And what we can see is different kinds of musical structure appear in different representations. So the first one, I think the easiest to see, is the middle one. The autocorrelation coefficients are tracking slow timescale change on the order of rhythm. And so what we see, for those of you familiar with Money, it's an interesting song. It starts off in 7/8, the meter 7/8, and then switches to 4/4 in the middle. And you can see very clearly the switch from one meter to another showing up in the autocorrelation. At the same time, in the spectrogram, we can see information having to do with pitch and with changes in instruments that are mirrored in the MFCC, which actually can be thought of as the low order values of the autocorrelation. And so, for example, we can see here at around 97, roughly 100, a saxophone solo starts, and we see the evidence for that saxophone solo in the MFCCs and in the spectrogram, but we don't see that at all in the autocorrelation. The autocorrelation is invariant to timbre, whereas these other features are picking up timbre and are invariant to timing changes. And so we can see that we can cover sort of the musical range of rhythmical time scales with certain features, and we can cover the fine time scale necessary to capture timbre. And if we mix these features together carefully, we might be able to learn something about musical structure. So for those of you who do machine learning, I hope there are some of you here, the first thing you might be thinking is, yes, but how on earth are you going to learn anything from such high-dimensional data? 1 minute of CD audio yields approximately 5.3 million values per minute. If we do a 512-point spectrogram computed with 50 millisecond frames, we get 8.6 times compression, so something over 500,000 values per minute. If we use something tighter, like just the 13-point MFCC coefficients, which tend to be very useful for speech, then we're down to having 15,000, 16,000 values per minute. But this is still a lot of data if what we're doing is trying to make a prediction about a song or about 30 seconds of audio. And so we asked the question, how do we find a lower dimensional feature set? How do we find a smaller feature set that still retains some of the important information? So our method that was published in 2006 in machine learning is to do kind of feature aggregation. We weren't the first to do it, but we were one of the first to actually look carefully at what size segments work well for music. And so, for example, these are the MFCCs for the same Pink Floyd Money song. And at the top are 1-second segments. So it's the mean of each value over spanning 1 second, and then 4-second, 8-second, 16-second segments. And it's also useful to keep the standard deviation around. So we fit a Gaussian to every row of that matrix over a particular time span. And actually, we can do more complicated things like fit mixture models. I mean, any dimensionality reduction algorithm we want to use, we could use here. But for the moment, we're talking about something very simple, just fitting independent Gaussians. And that raises the question of what's the best segment size. And to decide that, we need to have some sort of learning framework. So what we're going to do is talk about how we might learn. And once we can learn, we're going to talk about how we can decide what's a good segment size. One thing we notice, OK, so how do I motivate this? Spectral features that capture timbre, like is it a guitar, or is it a flute, or is it a human voice, are really useful only over relatively short time scales, because that's the span of a musical note or someone singing. I mean, if you take an entire song and look at these kind of timbre-based features, what you see is flute plus organ plus drum plus, you don't pull out any of the individual instruments, nor can you pull out enough structure to make reasonable predictions. So what we're going to do is train a classifier on individual columns, in this case, individual segments of means and standard deviations. And then we're going to vote over the predictions of these individual classifiers that work across segments, and we're going to vote and take a winner. Okay? And what we're going to ask the question, well, what's the right segment size, right? If the segments are too big, right, then we start to lose detail and we don't have enough segments with which to vote. If the segments are too small, then maybe we don't have enough data to learn anything from individual segments. Also, we have an explosion of data. We have too many segments to learn effectively. And so actually, there's a pretty good answer for this. We tested a range of segment sizes for 4 feature sets, Fourier transforms, real Kepstrel coefficients, but it's not important what the features were. And we tested 4 different learners, so we don't have a bias for which classifier we used. We used AdaBoost using 2 different weak learners, stumps and trees. We used a standard neural network, and we used a support vector machine on a 1,000-song, 10-class data set. And then what we did was we trained each segment individually, and then we voted for prediction. And the result is basically that the segment size between 3 and 8 seconds is optimal, which is a nice value to have laying around if you're, when you come to this problem later. And what you can see is that if you're looking at the accuracy of individual segments, actually, at least up to 30 seconds, you do get a gradual increase of predictiveness as you look at more and more data. So what I said about needing to keep the segment size small, at least for MFCCs, doesn't seem to hold. If you have lots of data, you should look at it. However, if you can vote, if you can look at multiple segments and vote on them, then we start to see an optimum appear. So this top row is showing the accuracy when voting across all segments. Now, if we have one big segment or a few big segments and we vote across it, we actually perform significantly worse than if we have, say, 10 3.5-second segments versus one 30-second segment. And there is a point where it falls off. So, for example, 1.8-second segments simply aren't predictive no matter how many of them you have. And this basic curve holds for, with different degrees of goodness of fit, holds for all of these feature sets and all of these learners, though they don't always all look quite that clean. So now I'm going to move on from feature extraction and close off feature extraction with the basic idea that where we started for our research was trying to take the simplest possible feature set we could, some spectral features, some cepstral features, and a few others for different simulations, and try to use a particular form of feature selection to find out which of these features are the most predictive, okay? As opposed to doing a lot of engineering and looking for exactly the right feature set up front. So how are we going to do this feature selection? We're going to use a very standard mechanism called boosting. And in this case, we used a version of AdaBoost, adaptive boost, from Freund and Shapir, 95. And the way boosting works is we build an initial model using a single weak learner. And in our case, what a weak learner is among the simplest learners you can imagine. We take one of the values from the feature set for all songs. Whoops, I went back too far. We take one of the values from the feature set for all songs, maybe MFCC coefficient number 4, okay, for all the songs in our training set. We sort that list of features, and we tried to see if by cutting that list at some point we can perform classification. So what can we do if we say if all the values less than 37.4 in this feature set are greater than or less than, would that give us a classifier? And of course, as long as we perform a little bit better than chance, it doesn't really matter. Being 60% wrong is as good as being 60% right, because we can always flip the sign for a two-class classification. Okay? And so what we do is we iteratively grab a weak learner, we identify wrongly classified points in a data set, and then very importantly, we boost these points so that the points that we were unable to classify are going to receive more attention, weighted by a weight for every data point for future weak learners. And we continue adding weak learners until we've reached an error criterion. And so you can see here a simple example of points drawn around a circle. You can see the equation. And our first cut does as good of a job as it can from separating red from blue, and it increases the probability, it increases the weight of misclassified points. And after many cuts, we see that we have only a few points left. AdaBoost and related boosting algorithms end up having the nice property of being large margin classifiers. And also, given the way that we're selecting these learners, such that each learner is tied to a specific feature, we're doing feature selection where our criterion for selecting a feature is based upon minimization of empirical error. So our feature set, when we're done, is going to be in order based upon our ability to minimize empirical error on our training set. And so what we can do is analyze the feature set and remove features that don't help us. We haven't automated that, but for example, we were working with a particular kind of feature called chromograms, where we look at pitch on the musical scale. And in running a couple of simulations with a reasonably large data set, none of these features were being selected as early candidates by the booster. So we said, well, it's not worth bothering with chromograms, and we throw away a number of points. In the interest of time, I'm going to skip the full algorithm for AdaBoost. It's not my research. I'm using this as a classifier. And in fact, I'm agnostic. I like the properties of AdaBoost, but I think that a next step is to design an algorithm that actually takes more into account some specific constraints having to do with how this problem is defined. So I'll skip that. So a couple of other observations. I've made some of these already, the first two. Oh, I see. The third one should say that it's slow to converge relative to SVMs. Somebody, some program made a spell check correction for me. Thank you. But it's in linear complexity with respect to the data set size. That is, we don't have a problem with explosion in terms of large data sets. So we can use boosting to look at huge data sets. We don't have a guarantee that we can minimize error with the same number of boosted features that we can for small data sets, but we also don't have this hard limit that we see with SVMs. And also, to learn multiple classes, for example, to learn one versus all genre, let's say we have 12 genre and we want to predict which genre a song falls into, we can do that using a particular form of AdaBoost, which builds independent weak learners one against all. So it's one learner is trying to learn rock against everything else, another learner is trying to learn jazz against everything else, and then it's combined as it's built into the algorithm. And frankly, as I said, I'm rather agnostic about the specific classifier we're using. We're using a version of AdaBoost that is known to have some problems, especially not being very good with noisy data. So I'm convinced that even within the framework of boosting, if we continue to follow the literature, we can improve that. Okay. So what we have, sorry, yes?
Sorry, I just to clarify. The voting scheme that you use for determining segment size, that's not part of the boosting procedure. You're using individual segments as your examples and their labels, or you're using the whole song?
That's an excellent question. So the question, I was asked to repeat the questions for the microphone. So the question was, when voting takes place, is the voting an intrinsic part of the boosting algorithm, or is it something that's happening after the fact, right? The answer is that it's not an intrinsic part of the boosting algorithm. We're voting using the predictions of the weak learners, okay? And furthermore, it's a very interesting direction for future research, because in fact, if you take the segments and treat them as statistically independent and then vote on them, you're throwing away a lot of information. And in fact, one important piece of information that you throw away is, let's say you have a 4-minute song that's labeled as raw, and so you have all of these segments, right? And it turns out that 80% of them are voting rock, but 20% of them keep voting classical, because in fact, there's this stupid classical thing in the middle, right? And so what you have is, in the standard boosting, these get treated as hard points, right? So their weight goes up and they get even more attention. And so what we're looking at now are ways in which to propagate information from segment to segment. And we've already tried the most simple method, which is literally to compute the weights for segments based upon a weighted score or even a standard mean of the weights for all the segments, right? So we have a weight for the difficulty of a point, which is a segment, and instead of looking just at that segment, we could treat the weight for that score as the weight of the difficulty of the entire song. And that actually does help, but we haven't had time to test it well enough to know how well it helps. And I actually think there are better ways to do this where we actually redefine the cost function of the problem to say, well, our cost function is not that we're trying to minimize error on a segment, but that we're trying to minimize error on some, we want to have some number of segments in a bag, work for us. So thank you for the question. I was going to mention that. So I want to talk about some results to give you an idea of what this approach can do. By this approach, I mean extracting features from audio and then training with boosting. The first task comes from 2005 and 2006, work done with my students, predicting genre and artist. So you're given the genre and you're given the artist for a number of songs, and then on a testing set you need to try to predict songs by the same artist or songs that fall into the same genre. Obviously it's a classification problem, so you can't bring in a wholly new artist and predict it because it was one of the bins of your classifier. So we actually use more features for these experiments, and for those of you that are familiar, you can read the list, and for those of you that aren't familiar with these kinds of features, you can safely ignore the specifics. And what we found was relative to, well, some of these are nearest neighbor approaches and quite old. Our approach for a very popular test data set is, as far as I know, still state of the art. I don't think anybody's done better than 83. In fact, this is right about where people are sitting around 80% on this data set if you ask people to say what genre these songs sit in. The task is to take songs from a 1,000-song data set and say, is this rap or is this country? And you can't say it's half rap and half country. And so, people disagree about what's pop and what's rock, etc. I think more importantly, this approach, when tested in there's a contest every year at a music information retrieval conference called ISMIR, called MIREX, Machine Information Retrieval Experiments or something like that. And they had an artist identification contest in 2005, and our approach, AdaBoost, the two AdaBoost approaches, one with the stumps I described, another using a simple tree building approach, which I don't want to describe now, performed very close to Dan Ellis's approach, and actually performed better then Dan's approach on magnitude. And Dan did significantly better on the US pop data set. Dan's a friend of mine, so I don't feel bad telling you that even he knows he overfit. It was his data set. And then they asked him if he could use it for the conference. He's like, yeah, of course we did better on US pop. We tuned our data set. You know, we tuned our hyperparameters on US pop. So I think effectively they're roughly equivalent. This is important to me because they spent a lot of time choosing the right kernel and spending time thinking about the right way to do this with SVMs. And since SVMs are clearly, I mean, they've been the state of the art for sort of standard classification for the last, what, 5 years? It's hard to come along with something like boosting and not compare it to SVMs and say, you know, you're in the same field. I like our boosting framework because of its ability to scale to huge data sets and because of its automatic feature selection. But it's nice to demonstrate that a serious and careful use of SVMs yields similar results. And in fact, the same data was used for predicting genre. The distinction is, I'm going to flip back to artist. For artist, we had 77 artists. And for genre, we only had 10 genre for one data set and 6 genre for the other. And now our approach, both of our boosting approaches significantly beat all of the other approaches on that. The problem with this task is both of these tasks, both artist prediction and genre prediction. One is they were defined as one versus all tasks. So as I said, a song had to fit in one genre and only one genre, which is kind of stupid, right? And also, we don't want to predict artists, right? I mean, of all of the information we're very likely to have from the MP3 itself is going to be the name of the artist. We don't need to spend our time predicting that. What we want to predict are more general information. So what I want to do is be able to look inside of a sound file and pull out a nice big vector of information that I know can be used in a supervised learning framework to predict some things, and also via using supervised learning and probably some dimensionality reduction, I can come up with an even shorter vector that really does a good job of encapsulating the sort of dimensions of change, sort of the musical space in which a song would sit. So what we looked at was using as labeled data some social tags. So Last.fm via its audio Scrabble interface allows researchers to go and do data mining and collect lots and lots of tags. And so we collected lots of tags for, I think, maybe it's on the next slide, something like 40,000 artists and their songs. And just to give you a feeling for what's out there, 77% of all of the tags have to do with genre, mood, or instrumentation. These are all things we can predict with acoustic features. Some of the things we can't probably predict very well are things like locale, which is surprisingly high, 12%. I mean, there is a Seattle sound, right? But a lot of this stuff is, you know, if there's a band in Iowa that's using the Seattle sound, we're not going to learn it's from Iowa, right? And then some of these other things like opinion or, you know, style, such as political style or humor, we're not going to predict. And some of these tags like seen live are utterly useless for us, right? So if someone has seen it live, or I own it, we're not going to predict that either. Here are the top 20 tags applied to the group The Shins, who I hope you all know and love. I know and love. I saw them just a few weeks ago. So you'll see actually some frustrating things if you're trying to pull things apart. We have indie, we have indie rock, we have indie pop, we have alternative, we have rock. Not entirely descriptive tags and very popular tags. I'm hard put to have someone define for me what's the difference between indie and alternative without just using examples of bands. Right? So what I should stress here is that the task here is to predict these social tags, right? But that's not the long-term goal, right? The long-term goal is to extract something from music that tells us what's inside the audio. We're using the social tag construct as a way to get an idea of how well we're doing. And in fact, even then I admit it's hard to know how well we're doing, but let's take a look. So the first thing we have to do is decide how on earth we're going to learn something from these tags. So let's take a look at one of them. This is the histogram of the tag rock. And what we're seeing is a histogram. This bin is the number of bands that had no label for rock. So there were 2 times 10 to the 4, right? And then we see, okay, then we see, like, so this is how many bands had 10 labels for rock. And at the end here, we see a number of bands that had 30 or more labels of rock, okay? And all of this is difficult to normalize because we have some bands that have massive numbers of labels and others that don't. And there are some normalization schemes that we use that are too arcane to describe here, but I'll let you know that we took care not to do kinds of normalizations that break things, and I would still say it's a hard problem. But what you can see is that, or what I hope you can see, it's easier to see on some other tags, is that it's not a clear distribution where we can say, okay, this is a bimodal or trimodal distribution. They're very jagged, okay? And so it's very unlikely that we're going to be able to predict the actual number of times an unseen song would have been tagged, right? Because some popular bands like the Beatles get tens of thousands of tags, and unpopular bands get a few tags, yet they both are good examples of a particular thing, like rock. So what we decided to do instead was build bins. We computed whether a band should fall into a kind of no rock category, where it had very few tags relative to other tags, some rock, or a lot of rock. And we did that for all the tags, and we didn't use any of these algorithms for choosing our bin boundaries to maximize our ability to do classification. We simply tried to divide each of these groups of tags such that we had roughly equal numbers of no rock, some rock, and a lot of rock. Okay? And we did it by just computing a 100-bin histogram, and then ticking across bins until we had grabbed a third of the data, and then a third of the data, and a third of the data. So very simple. And in fact, for classical, that was impossible because there just aren't that many things labeled classical, so we could only use 2 bins. Everything else was basically none or all. Okay? And so we used a simplified feature set, just MFCCs, log spectrogram coefficients, and autocorrelation coefficients. We're going to learn each tag independently. Okay, so we're not doing what we did with genre, where we say something is either rock or country. It's a lot of rock, maybe it's some country, maybe it's a lot of jazz, maybe it's no classical. And then later we're going to use the magnitudes of the weak learners to form more graded predictions. That is, instead of just pulling out from the learner a lot of rock, we're going to actually look at how strongly the learners voted a lot of rock and use that as a rough measure of how confident the learner is. This is a hack, and it's also something else that needs to be better integrated into the cost function of what we're doing. But in effect, the distributions don't support the kind of regression we'd like to be doing, nor is there enough data to really do the kind of ranking we'd like to be doing. So in a sense, we're doing the best we can with noisy data. And you can see what we have here. We grabbed 13 tags, all of them purposely to have to do with genre so that we could compare them to one another. There's no limit. We could look at music for jogging or whatever we want to. And we had finally 43,000 songs to learn from. And a few of the artists we had to throw out. They had no tags in these 13 classes. And then this left us still with quite a few artists. And what we see is that we don't learn. So these are the error rates for 3-class learning, except for the one that's marked with the arrow. So our ability to take a song in a testing set, an unseen song, and say whether it is none, some, or a lot of, say, jazz. Okay? So the error rates for songs are all sitting around 60%. Of course, chance would be 33%. And the classical one is much higher, but recall that it's 2-bin, not 3-bin classification, so that 90% is not comparable. So this is testing error using 1-fold to 5-fold cross-validation. So basically, by that I mean 80% of the data was in the training set, 20% was in the testing set. And we just let the model run and choose up to 2,000 weak learners. That doesn't mean it was done. It's just when we stopped the simulations. And we're not Google. So we didn't have, I'd love to let it run longer. I mean, it wasn't finished. This is just where we stopped so we could get the paper out the door. Okay? And probably more useful than looking at error rates, these are the top 40. Okay? So this is as meaningful as you want it to be. You can look for bad examples or good ones, but these are the top 40 classic rock bands as predicted by the magnitude of the lots of rock bin, okay? And what you see is that there are some largely there are some good examples of classic rock, like Steppenwolf and Creedence Clearwater Revival. By and large, I think it's pretty good, especially if you go down and look at reggae and compare. And then there are some really bad examples, not surprisingly as well. But by and large, we could have computed also goodness of fit on ranked order, but the data is so noisy, all we're going to get is some number, right? So I'm just showing you these as a kind of idea of what we're able to do. The electronic worked better, but that's not surprising, because for those of you that are electronic fans, electronica, I should have put, you'll see quite good selection of electronica. And the reggae is also interesting because we didn't actually have a lot of reggae stuff in the database. And so it selected, for reasons I don't understand, Bob Marley's not in there, for those of you who are looking for Bob Marley. But you know, all of these are reggae bands. We even come down and pick up bands that have reggae songs, like The Police. At the same time, I don't want to go out of my way to highlight successes. We can also analyze and find really bad fits, like, well, I don't think X is classic rock, for example. But by and large, we are able to learn a lot of this structure. It's also maybe interesting to look at some of the examples of these feature vectors now. Now I just pulled out 7 of the, by the way, I'm almost done. I want to leave room for questions. I pulled out, 8 of the genre, just to have them all fit. And I grabbed some examples. I didn't show you jazz and classical, by the way, because those always work. There doesn't exist, I mean, whenever you look at these results from predicting genre, everybody can predict classical, and everybody can predict jazz. So my list of classical and my list of jazz musicians is just perfect, right? It's just easy, right? So I didn't even show you those. But you can see, for example, number 1, Gustav Mahler is positive classical, and I know I marked the negatives in red, negative everything else. Wilco, another band I like. Now you have 2 points of data. You can predict my musical tastes, the Shins and Wilco. They show up as Britpop, which is kind of silly, but they also show up as classic rock, electronic, that's one of, you know, and then strong indie and rock. And then there's some serious failures like Tom Waits on the bottom. I'm not sure which discs were in there, but for some reason we think Tom Waits is jazz, which is very seriously only partially true, right? It's just only partially true. Another thing that I want you to notice is that these magnitudes, because we're not, our cost function does not, we're not learning a regression function. We're learning these bins, these classifications, right? There's no scaling at all to these values. This is just the weight, the strength of the sum of the weak learners, how strongly they predict whether something falls or doesn't fall into this bin. And so we say that Gustav Mahler is minus 3.145 Britpop, and that the Beatles are 0.001 Britpop. Those values are comparable, but we can't compare that to the magnitude to the column to the right. We could adjust them, we could pretend that they're Gaussian, we could adjust them to have a mean 0, standard deviation of 1, whatever we want to do, but in the end, these are intrinsically not interpretable as magnitudes. This is just to show you what's going on. Finally, to show you some nearest neighbors, if we use those vectors, actually all 13 of the genre, and we look at nearest neighbors, we can, for example, the last FM tags, to give you something to compare to. I should have shown you the top 40 for last FM as well to compare. I didn't have time. Fatboy Slim shows up close to the Prodigy and Basement Jaxx and Apollo 440. We also have Apollo 440 and Beck, which is a bit strange, but Chemical Brothers is okay. The Beatles for Last FM shows up next to Lennon and the Beach Boys and the Doors, but we have them near the Rolling Stones and Marvin Gaye and Eric Clapton. So there's a kind of reasonableness to these. My point would be in all of this is that we're certainly not going to get the right answer with quotes around it using our learning, right? But that's not what we're trying to get. What we're trying to get are some reasonable values for unlabeled music, and also some values for the kinds of information that doesn't tend to be labeled by users, so we can smooth things out. I mean, we have the web. We have all of this textual information anyway. We're just trying to get some values that seem reasonable and that are useful for describing musical content. And I think to that extent, these very preliminary experiments show that it works. Finally, if you want to see a little bit of There's no multidimensional scaling or anything else. This is just the values of the weak learners, just as I showed you in the red negatives and black positives of the previous slide. You can see where some bands show up. We couldn't show you the entire data set because it would have just filled the screen with black. But you see, as always, classical clusters together, just like it should. Gets itself out of the way so we can look at other things. And we see kind of reasonableness. As we move up in rock, we see rock bands show up. As we move down and to the right, we see serious electronica show up, and then the mixture of stuff in the middle. What we want to see is the same kind of nice, clean, low-dimensional space when we look at all of these classifiers together. And we tried it, and we get kind of nice 3D clustering where the jazz sits over here, and the classical sits over here, and then everything else is kind of sort of working. But in the end, that's not how to do that kind of visualization. We're not there with this model. This model wasn't designed to do that kind of visualization. And I think if we really want to do 3D visualization of music, we need a cost function that is better suited to preserving the kinds of distances between near neighbors that we need to do visualization. That said, I think there's a kind of reasonableness that's preserved. It certainly looks as good as these. You see these kinds of graphs in music information retrieval papers all the time, right? If you read these sorts of things, and this is as good as all the others. So it's whatever. So my conclusions. What I'm trying to propose, or what I have proposed, is what I think is a simple framework for machine music listening. We extract audio features, we segment those into chunks, and then we do ensemble learning on those chunks to try to predict some social tags. Where this can be interesting, I think where this could be interesting for, I think the model as it is could be interesting for a company to jump down a little bit, for companies like Last.fm or Pandora, the music recommenders. But where this becomes interesting for a company like Google is when you start to say, I'm not only worried in the kinds of features that are good for selling music to people, I'm interested in having a huge vector that I can then map onto text so that I can generate a bag of text that sits with every audio file. Okay. The kind of bag of text that you generate to sit next to every audio file on the web for something like Google for a search engine may not be the same kind of bag of text that you want to sell music or to recommend playlists for people. So what we could talk about doing is, instead of doing these 13 tags, the idea would be to learn lots and lots and lots of things about music. You can think about learning with existing signal processing techniques and learning to extract 100 the probability that a given musical instrument pulled from a huge number of musical instruments. Are there female voices? Are there male voices? And then lower level statistical measures of how the music was recorded, its source, so that what you can do is generate a large numeric vector, and because you've trained on text tags, have a reasoned way to go back into the space of text, which of course is where Google's strength lies, is in doing text-based search. Okay. There are limitless ways to improve this. This is very much a first step. First, we're doing classification over some, none, some, and a lot. But what we really want is regression or ranking, because that's what we want in the end, is to look at how these relate to one another in terms of their magnitudes. So it's clear that we need to do something else with our learning. We also want to try to do some regularization so that we can take advantage of the idea that, as you rightly questioned, our labels are done on the level of a song. Almost all of our information that has to do with music is information relating to a song or an artist. Yet the descriptive quality that we get from audio feature extraction sits on the level of frames of data. And so we have a mismatch that we could actually exploit to speed up learning. Finally, we have a number of features that are derived from a very high level of looking at how audition works and how music works. These are what could only be called the simplest possible features you would extract for an early start. And I see two directions to move with feature extraction. One of them comes from looking more closely at how rhythm and how pitch are represented in the audio in the auditory pathway, and also in using unsupervised dimensionality reduction algorithms for extracting features that are predictive for a particular task. And also just the idea of saying, if we have the computational resources, just extracting lots and lots of features. But finally, with this, what I think is relatively simple machine learning, we can, in fact, listen to audio and learn a lot about musical content. And we can, in fact, embed songs and artists in a rich space. And we don't need to have all of the collaborative filtering or expert-based labeling that we get from Last.fm and Pandora. This works. It works with state-of-the-art machine learning, and it could work better. And there are clear paths for getting there. But I think, a hint to Google, this kind of research is important for companies that want to know what's going on with music on the web. And so that's why I wanted to give this talk. And I think that's it. Just citations. This was just submitted to Izmir, some of this. This was in machine learning and another Izmir paper, and there's my email address. So thank you for your patience.
So you talked about extending it to use properties of the auditory system. What about more properties of music? Models of melody or rhythm?
Yeah. So the question was that I talked about using properties of the auditory system. What about more properties of music? Yeah, in fact, we were talking about this at lunch. By and large, the kinds of things people label are timbral based. I mean, timbre features tend to work really well for things like genre, and I like to jog to it. But there's a whole class of similarity measurements that people make that we can't do with low-level features. And the most important one, or I guess the most illustrative one, is that of cover song recognition. So you like a song and you want to hear other versions of that song, right? To answer that question, I actually have a web page about this with a bunch of different versions of these are a few of my favorite things. The Sound of Music song that was then done by John Coltrane. As it turns out, if you go to iTunes, there are like 50 versions of this song, right? You just download the 30-second snippets. And there's no timbral similarity. There's not even rhythmic similarity if you consider that the John Coltrane version is in 6/8 and the original version is in 3/4. The different instruments are used. Some of them are, Barry Manilow sings a song. All of these things. Yet, for people listening, there's a clear and obvious similarity between all of these songs. They're the same song, right? To recognize this, we actually need both. We need a clear understanding of how people are tracking pitch and are extracting this long timescale information that has to do with melody, and at the same time, we need the musical constraints. So the way I think about this is we need what in speech recognition would be a language model. We need to have some higher level constraints on the kind of learning that we're doing. Furthermore, we start to treat music then like a real sequence, which is what I really like doing. I mean, right now we're taking frames and throwing them in a bag and shaking them up. But if you want to talk about a cover song or something like that, then you have to really care about how the music evolves over time. And I think if you move into that area, then you have to care a lot about how music works. There was another question.
About the step you did pick the optimal segment size using coding.
Yes?
Was it necessary to do that, or could you have just thrown in all the segment values into your boosting framework and just pick the segment size as the classifier at that segment?
Okay, so the question was, when we optimized for the segment size and our segmentation, would it also have worked to throw all of the segments into the booster and just let the feature selection of the booster pick out the right segment size? In principle, it would work to throw them at the booster. In practice, when you're not Google, you don't have the computational resources to do that. So when you move down to 1 or 2 second frames and you have a large data set, you've got a lot of data. Also, the feature selection part of boosting, what we're doing is something really naive. We're treating a feature as a single value from an FFT or a single value from an autocorrelation. So it's very easy for the booster. These are very, very weak learners. And so in the end, when you analyze the order of the boosters, a whole chunk has to fail before you can say, oh, right, I can throw away this feature set. So what I highly suspect is that the booster would pick, it would like MFCCs, So it would pick MFCCs from all of these different time scales because they're nice, they're very descriptive for timbre. And then it would start picking spectrogram coefficients for all of these different time scales. And you wouldn't really see a clear preference of one time scale over another. Or it wouldn't show up in the first 5,000 weak learners, right? So in practice, it might not work at all. We could try it. It'd be cool if it worked. Yes?
What about movies?
The question was, what about movies? This is an area of great interest for me and also some people in the lab where I am at University of Montreal. Yeah, you know, I think of music because it's where a lot of my training comes from. And I actually think that music is a really cool playground for learning about how to treat video because you have the sequentiality to it. And once you've understood this time sequence, then you've already got tools for extracting information from other time series. And so, I mean, I think that there's a kind of lifting property that would take a lot of this research and map it on to video. I think what would get popped in and out of the features and, you know, gajillions more cycles of processor time. I'm also interested, I mean, just in terms of my research, I'm interested in these all of this new research that's happening with, you know, multiple streams of information and multimodal learning and, you know, ways of trying to bring together these different information streams and pull one off of the other. But other questions? Thank you.